3-2, solving systems algebraically. So in the previous section, we talked about graphing two lines and seeing where they intersect in order to solve a system of equations. In this section, we're going to take the guesswork of trying to make a graph, and we are going to actually solve these systems using algebra. Okay, so our objective for this section is to solve linear systems algebraically. So our essential understanding is that we can solve a system of equations by writing equivalent systems until the value of one variable is clear. Okay, there's a couple different ways to do this, and we'll talk about both of them. Okay, after we get one variable, then we can substitute to find the value of the other variable, or variables, whatever we have. Okay, so let's take a look at this little warm-up problem here, where we have a couple different jobs. Okay, so you're looking for a job, and your search has yielded you two jobs. Okay, we have store A and store B. So store A, you're going to make $35 a day plus 10% commissions. Store B, you're going to make $10 a day plus 18% commissions. Okay. So the question is, what whole dollar amount of per day sales would make it more worthwhile to work at store B? All right, so how are we going to do this? Well, the first thing is we're going to have to do is we're going to have to set up a system of equations. So my first equation for store A would be the amount of money that I make is going to be equal to 10%, change to a decimal, times your sales, plus $35 a day. My second equation for store B is going to be 18% times your sales, plus $10 a day. So what I want to do here with this problem is now, because both of these are equal to y, all right, in order to find when it's more worthwhile to work at store B, which are getting paid less per day but a bigger commission. So you got to find out what amount of sales is going to give you the most benefit for that bigger commission. Because both of these equations are equal to y, I can set them equal to each other. So I would get 0.18x plus 10 is going to be equal to 0.10x plus 35. Subtract 0.10 from both sides. Okay. And we're left with 0.08x plus 10 is equal to 35. And subtracting 10 from both sides gives me 0.08x is equal to 25. Divide by 0.08 to get my answer, which is 312.50. Okay. That was a system of equations. Okay. And we have figured out that at $312.50 of sales, it is better for you to work at store B versus store A. Okay. So what we're going to be doing today is we're going to be looking at other types of systems and see how we can solve them. Okay. So the first method we could use, which we actually just did, is the substitution method. Okay. So we can use the substitution method to solve a system of equations when it's easy to isolate one of the variables. Okay. This is key when it is easy to isolate one of the variables. If it's not easy, there's other methods we can do. All right. After isolating the variable, substitute for that variable in the other equation. That's important too, right? We don't want to substitute something back into the same equation. We always want to substitute back into another equation. Then we're going to solve for the other variable. Okay? So looking at my first problem, I want to decide, is it easy for me to isolate one of the variables? Well, looking at this variable right there, y, it's by itself. That's what I'm looking for. I'm looking for a variable equal to something or a variable with a coefficient of 1. Okay. So taking that bottom equation, that 2x plus y is equal to 10, all right, I want to get y by itself. So I'm going to subtract 2x from both sides. That leaves me with y is equal to negative 2x plus 10. Okay. Now, I'm going to rewrite my first equation. 3x plus 4y is equal to 12. The key to substitution is that I am going to replace y in my second equation over here. Okay, I'm going to replace y with something having to do with x, because I can't solve an equation with two letters. Okay, so I have to get rid of one of the letters, and I can do that by substituting negative 2x plus 10 for y, because they're equal to the same thing. So that means I can take this value right here and plug it in for y right there. Okay? So let's do it. So 3x plus 4. But instead of writing y, I write my equivalent expression, because y is equal to negative 2x plus 10. So I put negative 2x plus 10 is equal to 12. Now, I have an equation now that has only x's in it. Now I can solve it. 3x, distribute the 4, minus 8x plus 40 is equal to 12. The 3x and the 8x are on the same side, so all I have to do is combine them. I got negative 5x plus 40 is equal to 12. Subtract 40 from both sides to get x by itself, and we get negative 5x is equal to negative 28. Not going to work out perfectly, but that's okay. Divide both sides by negative 5. And we have x is equal to 5.6. Okay. Now that we have x, okay, my system is half complete. Remember what the point of this is. The point of solving a system is to find the point where these two lines intersect. So in order to do that, I not only need an x coordinate, but I also need a y coordinate. Okay? Well, I have a couple choices. Since I know x, I could put it there, but I already have an equation that has x by itself on one side and y equal to that expression. So I'm going to use this expression right here in order to solve for y. So y is going to be equal to negative 2 times 5.6, which is what x is equal to, plus 10. So that gives me negative 11.2 plus 10. So y is going to be equal to negative 1.2. To finish up, I want to write my answer as a point. So we have 5.6 comma negative 1.2. And that is the point where these two lines intersect. And that was solving an equation using substitution. Okay. Let's look at a word problem. Okay. A music store offers piano lessons at a discount for customers buying new pianos. The cost for the lessons and a one-time fee for materials, books, CDs, software, are shown in the advertisement. So here's our two data points. 6 lessons is going to be equal to 300. 12 lessons is going to equal to 480. So with those two pieces of information, I can figure out how much the lesson is and how much the one-time fee is. Let's call each lesson X, and let's call my one-time fee Y. Okay, so let's use my information that 300 bucks is going to be 6x, 6 lessons, plus my fee. Same thing for the second one. At $480 is going to be equal to 12x plus my fee. Okay. So now you have a couple choices. Now I can solve this using substitution. I could also solve it with my next method, but we haven't got there yet. So let's use substitution again. Let's isolate that y right there. Okay? That y in the first equation, this guy. All right, so get it by itself. I'm going to subtract 6x from both sides. So that's going to leave me a new equation with y is going to be equal to negative 6x plus 300. Okay? So because y is equal to that, I can substitute this new expression into my other equation. Now that's important. You don't want to plug it back into your original equation. And you want to plug it back into the new equation. Okay, so let's do it. So that says that 480 is going to equal to 12 times x plus, well, plus negative 6x, so minus 6x plus 300. Combining like terms gives me 6x plus 300. Subtract 300 from both sides to get x by itself. So we have 180 is equal to 6x. Divide by 6, and we get that x is equal to 30. A little more room. So x is equal to 30. Now that I have my value for x, I can take it and plug it back into this expression right there in order to get y. So y is going to be equal to negative 6 times 30 plus 300. So that's going to be negative 120 plus 6 times 3 is going to be 180. All right, whoops. Plus 300 gives me my 120. Okay. So my answer to my system is 30, comma, 120. Now, even though this is the point where my two lines intersect, it makes a little bit more sense to go back up to my original problem and say that the cost of each lesson is going to be $30 and the one-time fee for material is going to be $120. So in this case, it makes a little more sense not to leave the data as a raw point, but to sort of let you know which one is which. Okay. Next. Okay, we can also use the addition property of equality to help solve the systems of equations, right? If you add a pair of additive inverses or subtract identical terms, you can eliminate a variable. My point is to get rid of one of the variables. In this equation right here, there is no letter by itself. There's no variable with a coefficient of 1. So it doesn't make sense to try to isolate a variable and use substitution. So in this case, we're going to try to use elimination. So we are going to add these two equations together. The addition property of equality says if I add the same thing to one side, if I add something to one side, I have to add the same thing to the other side. Well, 4x plus 3y is the same thing as 16. So if I add 4x plus 3y to the left side of the top equation and 16 to the right side, I'm still adding the same thing to both sides of the equation. And that lets something really powerful happen. Okay? I'm just going to do it right over here. Okay, so if I add these two equations together, the x's will go away. 4x minus 4x, those cancel out. And that's good. That's what we want to do. We want to make sure that our new equation that we are left with has only one letter. If it doesn't, you can't solve it. So 2 and 3 gives me 5y is equal to 25. And dividing both sides by 5 gives me that y is equal to 5. That's great. All right. Now take 5 and plug it back into either one of my equations, right there or right there. I suggest the top one because it looks a little bit easier. There's no negative sign. The numbers are a little bit smaller. It does not matter which one you plug it into as long as you work it all the way through. 4x plus 2 times 5, which is y, is equal to 9. So 4x is equal to 10. Sorry, 4x plus 10 is equal to 9. Subtract 10 from both sides. 4x is going to be equal to negative 1. Dividing both sides by 4 gives me that x is equal to negative 1/4. It's okay to get a decimal. It's okay to get a fraction. Okay. My answer then becomes negative 1/4, comma 5. Okay. And of course, remembering that that is the point where these two lines intersect. Okay. And that is elimination. So we've looked at substitution, we've looked at elimination. Okay. In both of those cases, it was pretty easy. Okay, back here, it was pretty easy to substitute for y because y was by itself. And here, it was pretty easy to eliminate x because they were opposite of each other. The problem happens is when one of those two things doesn't happen right at the beginning of the problem. Okay, so what you're going to have to do this time is you're going to have to change your system into an equivalent system. Okay, so when you multiply each side of one or both equations by the same non-zero number, the new system and the original system have the same solutions. The two systems are called equivalent systems. So you can do this to change a system into something that has an additive inverse. Okay? Multiplying any number by a system is going to keep it the same. So here, looking at this problem right here, no letter is by itself. Nothing is gonna, if I add these two systems together, I'm going to get 5x 12y is equal to negative 1. That did not help me. That did not help me at all. I still have x, I still have y. So I can't just add these two equations together. The idea is to multiply the first equation by something, to multiply the second equation by something, and to get my answer to have two terms that are additive inverses of each other, so that way, when I do add them, they can cancel. So looking at the x values, I see a 2 and a 3. So I can multiply the top equation by 3 and the bottom equation by negative 2. That would turn the x term into negative 6x. Or I can do the y term. I can multiply the top equation by 5, the bottom equation by negative 7. And that would give you the same additive inverse for the y term. There, you don't have to remember those numbers. It's nothing specific. You can multiply by anything you want. But you, of course, want to make it easy on yourself and not pick not pick really big numbers, because then you're going to make the question a lot harder. So let's do this. Let's take the first equation and multiply it by, take this whole equation and multiply it by 3. So doing that gives me 6x plus 21y equals 12. Okay. Now, the goal is, of course, to get the x's to cancel. So I'm going to multiply equation 2. I'm going to take this whole equation and multiply it by negative 2. That gives me negative 6x minus 10y is equal to positive 10. Now, when I add these equations together, I get 11. The x's cancel. I get 11y is equal to 22. Dividing both sides by 11, y is going to be equal to 2. Okay. And now that I have y, I can plug it back in to either any equation. I could plug it back in there, or back in my original two equations. It doesn't matter. Okay. I am going to choose to put it back into the equation that looks the easiest to me, and that is number 1, because it's got all positives and small numbers. So 2x plus 7 times 2 is going to be equal to 4. So that's 2x plus 14 is equal to 4. Subtract 14 from both sides. We have 2x is equal to negative 10. So x is equal to negative 5. And that is my answer. That is the point where these two lines intersect, negative 5, 2. Okay. Now, sometimes when we solve a system, it doesn't always provide us with the unique solutions. Sometimes we get infinitely many solutions. Sometimes we get no solutions. When we get infinitely many solutions, that means that we are graphing the same line. Okay? When we get no solutions, that means we're graphing a pair of parallel lines. And we can easily tell by looking at these equations, and when I add them together, I get 0x, 0y is equal to 0. Okay? Because we have something that is true, this system represents the same lines. So the system in A has an infinite number of solutions, as opposed to the system in B. X's cancel, y's cancel. We have 0 is equal to 16. That is not true. Okay, so this has no solution. These two lines are parallel. They have the same slope and different intercepts. Okay. Very common to have word problems like this with a system of equations. I'm not going to go through this whole one. I just want to set it up. Okay. A student has some $1 bills and $5 bills in his wallet. He has a total of 15 bills that are worth $47. So let's set that up. $1 bills are going to be X. $5 bills are going to be Y. Okay. So that is, he has a total of 15 bills in his wallet. So X plus Y is going to be equal to 15. $1 bills, last time I checked, were worth $1, right? We don't have to write that though. Right? Plus, $5 bills are worth $5 to give me a total of $47. Okay. This system seems like it would be easy to solve with substitution. It also would be easy to solve with elimination. The trick to solving systems of equations is to look at the system and figure out which is the easiest way to do it. If there is a variable by itself, think substitution. If there is a variable opposite, an additive inverse already there, or if it's easy to turn something into an additive inverse, then you should think elimination. In this case, neither one would be easier than the other. It is a pretty easy system to solve. Okay. This word problem, which you'll probably see again on the chapter test, okay, is a little bit harder. Okay. So looking at this, we have to remember a fundamental equation, right? That distance is equal to rate times time. Okay, that's going to help us. So distance, 880 miles to Des Moines and 880 miles back. The trip there was with the wind. Okay, it took 11 hours. So I know my time. Okay, all I need now is my rate. So I have to think about this, is that when you're flying in a plane or when you're going up a river or down a river in a boat, right? If you are going with the wind is making you faster. So you would add those two speeds together. Okay? On the other hand, on the way back, which takes 22 hours, we are going against the wind. So the wind is making you slower. Okay? So my system of equations would look like this. Distributing the 11 and the 22 would give me 11x plus 11y is equal to 880. 22x plus 22y is equal to 880. Not plus, minus 22y. Okay? So I see here that the y values are opposite of each other, and I could very easily multiply the entire top equation by 2, and that would give me an equivalent system that I could use to solve this problem. Okay? Then once I got the value of y, all I have to do is plug it back into either one of the two equations to get the value of x.